Problem number 2. This one, again, fairly simple process. This one's a little more interesting. We're following a curved path from A to B. 2 moles of an ideal monatomic gas go through this thermodynamic process from B to A. And we're given the volume, V1. And we're given that this curved path is a special curved path. It's an isotherm. The temperature is constant and equal to 400 Kelvin, all along that path. And that's all that we're given. We also know from the curve, from the PV diagram, that there's a relationship between the 2 pressures. One is half the other one, but we don't know about any relationship between the volumes. So let's see what we can fill in. I'm going to make tables like I always do for the states, A and B, and for the process going from B to A. So let's fill in the given information. The volume is given at A, excuse me, 8.3 times 10 to the minus 3 cubic meters. And the temperature, 400 K, make sure it's in Kelvin. And one thing we can also do is jump to state B, because we know that both A and B lie in the same isotherm. So I'm going to fill in the temperature for B. All right, so I know 2 things here, volume and temperature. So I can solve for the pressure at A using my ideal gas law. Two moles, 8.31 joules per mole Kelvin. Temperature has to be in Kelvin. It's 400 Kelvin. And 8.3 times 10 to the minus 3 cubic meters. That gives us a pressure in pascals. 8 times 10 to the 5th pascals. I'll go ahead and put that in my chart. I can use the relationship that was given in the PV diagram between P at A, P1, and the pressure at B is half of P1. So I can go ahead and put that in here. 4 times 10 to the 5th pascals. And now I can solve for V at B using my ideal gas law. And the pressure was 4 times 10 to the 5th. So I get 1.66 times 10 to the minus 2 cubic meters. So I've got most of my information filled in for the states. The only thing I didn't is the internal energy, U. I know the temperatures, so I'm going to go ahead and fill those in. Because this is a monatomic ideal gas, three halves nRT. We had 2 moles. Our gas constant, 8.31. And our temperature has to be in Kelvin. And what do I get? because I didn't solve for it ahead of time. You know why I didn't solve for it ahead of time? Because I was really interested in the change in internal energy, delta U. And if the internal energy is only dependent on temperature, then these are going to be the same. And so my delta U is going to be 0, because the final minus the initial is going to be the same. But since I started finding it, let me go ahead and punch in my numbers. I get 9,972 joules. And that's going to be the same for the other one. Okay, so let me put those in there. And when I take a delta, I get 0. So that's one thing to be aware of. Isothermal processes, when the temperature does not change, the internal energy of the gas does not change. It only depends on temperature for an ideal gas. All right, let's take a look. What's next, Q or W? Work done. We're given the curve going from B to A. Work done is the area under that curve. You have to be able to integrate to figure out the area under that curve, but they'll give us the formula in the book, so we can use that to find the work done. The work done for an isothermal process, nRT times the natural log of V final over V initial. So we can use this. We can use this equation. Where does it come from? It's the area under the curve. How do you find the area under a curve? You integrate. And this is the solution. In our case above, because the pressure was constant, we didn't have to do a fancy integral. We knew the area was just the length times the height of the rectangle. But in this case, because it's changing, the pressure is changing as we go, we have to integrate. Okay, so this is it. We can use that, and I'll plug in V final, 8.3 times 10 to the negative 3. V initial, 1.66 times 10 to the negative 2. And what do we expect the answer to be? Positive or negative? The volume is getting smaller. The gas is being compressed. So the system is doing negative work, or you could think of it as the environment is doing work on the system, or the system is doing negative work on the environment. Anytime the volume gets smaller, the work done by the system is negative. And it should work out that way if you punch in the numbers correctly, because this is the natural log of a number less than 1, which is going to give you a negative number. So I get negative 4608 joules. And now I know delta U, I know W. I can use my first law of thermodynamics. The change in internal energy is equal to the heat minus the work done by the system. So Q is equal to W, because delta U was 0. And I can go ahead and put that in, negative 4608 joules. And again, let's think about that for a second. We went from B to A. We compressed the gas. Normally, when you compress a gas, it heats up, going from B to A. But this gas did not heat up. it stayed at the same temperature. We did this along an isothermal process, with an isothermal process. So normally you compress a gas, it heats up. In this case, it didn't. So what must have happened? Heat had to have come out of our system. We had to have pulled heat out of the system in order to keep the temperature the same as we compressed, as we did work on the system. So Q has to be negative. That makes sense. Heat had to come out. The sign of W has to be negative because the volume gets smaller. We did work on the system. So those make sense. And anytime we have an isothermal process, delta U is 0 because the temperature doesn't change. So I think this makes sense. I want you to get in the habit of, once you get an answer, think about it for a second. It's very easy to miss a minus sign. Think about it. Make sure it makes sense. Now we'll do one more. We'll do a process that's a little more interesting. They keep getting more interesting, don't they? Of course they do. Okay, let me set that up for you.